Alright, this is Moments in a Bridge worksheet A and also B on the other side, but we're going to start with A right here. And not going to lie, this is a kind of confusing. It's simple, but it's a little weird if you've never seen this stuff before. It's simple algebra, but we're going to walk you through this and just kind of help you out. So a couple things you have to establish first. First, right here, let's just to help conceptualize this, we have different planes here. We've got our axes. We have our y-axis right here, and this is our x-axis. So this one would be positive, this one would be negative, this one would be positive, and this one would be negative. That's going to just help us kind of think about how this all works. So luckily, we really don't have to worry about the x-axis very much in this one. This one, there aren't any forces in that direction, so it's half the work is done for us, which is really convenient. The thing we're really going to worry about is the y direction. So here we've got a bridge, we've got a load or a beam bridge, and point A, B, and C. So what's going on here is you've got these 2 points are supporting what's in the middle here. It's a 5-foot distance from A to B, and then 10 feet from A to C across the whole span. So first, this one right here is called a pinned joint. So a pinned joint is locked. So it doesn't like to move up, doesn't like to move left or right. This one's locked in all directions. So it's going to have some reactions if there's any stresses on it. Now, because bridges, like we learned in class, do expand and contract a little bit depending on temperature, engineers have to consider that, and they have to leave at least one joint so that it's free to expand and contract. So this is a rolling joint here. So this bridge, as the temperature heats up, it'll roll on that, and as it gets cold again, it will kind of contract back down, just a little bit. But enough that if it were a fixed joint, it would cause the bridge to buckle and likely collapse. So right here, this one does not like to move up or to go down. It likes to be just right where it's at, but it is allowing our y direction, so it does go back and forth that way. So there's 3 steps. So the first step in this is to draw a free body diagram. Most of that's done right here. We're just going to add in a couple of values here that are variables we don't know yet. So for A, in this direction, I'm going to write this R, A, X. So that means it's reaction force at point A in the X direction, like that. And then over here under A, I'm going to say this one, that goes up, and technically I should put a little slash in here, like that. This is going to be R, Y, or sorry, R, A, Y. Ray. And then over here we're going to put this in here, and this one is a reaction here, little slash. This is R, C, Y. So we've got those 2 reactions, and what a reaction is this force right here is pushing down. I'm just going to use this right here, and this is force, so I'm just using force B, Y. So that means this weight right here is pushing down at that much, and then these 2 are pushing back up. So it's kind of like it's standing on 2 legs, like a table here. So I put a 200-pound block on a table, and one leg takes some of the weight, and the other leg takes the rest of the weight. So not too bad. So now what I'm going to do is also I need to include this one. This is an R, C, X, and that one is kind of a funny one because this one is not bolted down in that direction. It actually doesn't exist. So just know that this one's going to be non-existent when we get to that point. Alright, so first thing we want to do, we've got after we're drawing a free body diagram, like we've done here, is we're going to draw we're going to figure out the sum of the moments. So the sum of the moments is kind of a tricky thing to conceptualize. right here, and it's always about the pinned joint, so about the triangle. So the triangle right here, this pin joint, you can think about this as if it were a lever. So right here, this is trying to twist around because this is being pushed down right there at that point. Technically the same thing is happening over here, but we're just going to isolate just A. So right here, it's pushing down, but this side at C is pushing it back up that way. So we've got kind of two levers. One lever that's being pushed down, and then one that's being pushed up. And the resultant force at A, which is trying to twist that way, is going to be 0. So down here into the space, I'm going to just draw a line right here in the middle, because we just need to do half on one side and the other half on this side. I'm going to solve for the sum of the moments about the pin joint about A. So this symbol is sigma, and that just means add everything together. So the sum of the moments about point A are equal to the moment of that goes to sorry, not the moment, but the torque. So the torque, which is tau at point B, plus tau at point C. So it looks a little wonko, but what we're going to do now is just insert some things that we know. And where we're going with this, by the way, the reason we're doing this is because it's going to tell us a couple of values we don't know. Right now, we don't know what RAY is, and we don't know what RCY is. Those are kind of our most important ones. You can probably tell just by looking at this that if there's 200 pounds here, that there's going to be 100 pounds in both sides, which is correct, but we're just going to show how to mathematically prove that. Because in engineering, most problems are not going to be as simplified as this one. Alright, so I'm going to zoom in a little bit here so you can see what I'm doing. It's a little far out. So I've got that right there, tau B and tau C. So I'm going to start plugging some values. So we know that this, in order to work, because this isn't moving, the sum is always going to be equal to 0. So I'm going to put 0 in here, is equal to tau of B. So this is the torque about B, and in this case right here, this is a negative value. This is pushing in the down direction, so it's a negative 200. So FBY is negative 200, like that, pounds. And I'm going to pop that in here, so negative 200 pounds times, and then it's the distance from here to there, which is 5 feet. Awesome. Sorry, my handwriting is not the greatest. And then plus, and then this one we don't know. We don't know what this force is going to be, which is going to be RCY. This is the torque from A to B, so it's the full distance and the force that's being pushed up right here, and we don't know what that is. So I'm going to write that in here, RCY, and then times the full distance, which is 10 feet. So basically what that says is these should equal the same thing. Well, basically together they should equal 0. So I'm going to type, or not type, I'm going to crunch that out again. So 0 is equal to negative 1,000 foot-pounds, and yes, that's a unit, 1,000 foot-pounds, plus, and then RCY, and 10 feet. So now we can kind of simplify this a little bit. I'm going to bring this over, so add 1,000 foot-pounds to both sides, and I get 1,000 positive this time foot-pounds is equal to RCY times 10 feet, and I'm going to do some I'm going to divide both sides by 10 feet, and that cancels out feet here, one of the zeros, and then both of these are gone. So that means 100 pounds is equal to RCY. Boom, and that is my answer right there. So now I know that this is positive as well, because it's pushing it up. So I'm going to say RCY is equal to 100 lbs, or pounds. Okay, so that's half the problem right there. The next half is going over here, and we're going to figure out the sum of the forces in the y direction, because we know this one, we know that one, but we don't know that one, which is Ray. So same kind of idea here. I'm going to go over here and I'm going to write in the sum, or sigma, of the forces in the y direction, so just going up and down, is equal to 0, because the bridge isn't falling, nor is it floating up into space. So we're going to use that assumption to do the rest of this. So I'm going to plug in what I do know. So I'm going to say 0, because that is equal to 0, is equal to the sum of RAY plus RCY plus FBY. So FBY, what that is so it's this reaction plus this reaction and this force. And just, you know, force and reaction, they're both forces, but it just makes it easier to think that one is opposing. So this one's the force that's going in, and this is what's opposing it. So I can plug in a couple of these. So I've got 0 is equal to RAY, which we don't know yet, plus RCY, which is over here. We just solved that one. 100 pounds plus FBY, which is negative 200 pounds. Cool. So what I can do now is I can say 0 is equal to RAY, and then plus, and this right here, or whatever, it's basically 100 plus negative 200, which is still negative 100. Oops, sorry, I wrote that kind of weird. Pounds. And then I can basically just flip that out to the other side, add 100 to both sides. Cross cancels. And then that means 100 is equal to 100 pounds is equal to RAY. So that is your answer there. So we've got RCY. I'm sorry, this looks so bad. Pounds. So cool. And those are our two answers that we need for finding the moments in a bridge and all of the forces. So right here, FBY, I can write that one in. FBY is negative 200 lb, so pounds. RCY was 100 pounds. RAY is 100 pounds. RBX, which is the reaction force right here, because there's no force pushing into it, it's going to be just 0. So there is a reaction force there. It's just 0. And then RAX, RBX, that was the first one. RBX, this one is 0 as well, as for the same reason. There's just nothing's going into it, so nothing goes out. And then RCX, because this one does not have, it doesn't oppose in that direction, it just doesn't exist. So we simply put in that. So that doesn't matter. Cool. And that is how you do the first one on side A. So not too shabby. Probably a little bit confusing, but we've got it so far. So now I can flip over to side B. And side B is a little bit trickier. It's the same exact process. The only difference now is that it's not in the middle. So kind of like we did with the last one, we can infer that because this is not in the middle, that both sides of these are going to be at an equal amount. So if there's 3 feet on this side and the full thing is 9 feet, that means we can use a ratio just to kind of guess this beforehand. If there's 300 pounds and the ratio is 1 to 3, that means one of these is going to get 3 times as much as the other side. Or, well, sorry, a third will be on one side and the other 2/3 will be on the other side. So over here, this one is going to end up being 2/3 of the weight because it's a shorter distance, so that's going to be 200 pounds, and then this other side should be 100 pounds, and I'm pretty sure we're guessing that right. But we need to prove it. So first step, just labeling all of the free body. So we just got to make sure we draw this all correctly first. And I'm going to draw in here about point A, R, A, X, which goes that way. And then this one is R, A, Y. And then right here, this is going to go down. And this is F, B, Y. And while I'm up here, I'm just going to write this in. It's negative 300 pounds because it's pushing down. And then at the C, right here, there's a reaction going back up. And this one is RCY. And then there's also a reaction here, which is, again, non-existent, sort of. So it's RCX. And that one's just going to be 0 because this is a or non-existent because that's a rolling joint. Okay, so we got that, and all of our other things are drawn for us, which is nice. I'm going to draw a line down the middle of this again, just to keep my math on 2 different sides. And step 1 is figuring out my sum of the moments about point A. So that's this one right here, sum of the moments, which is this twisty force or whatever, pretending that this is a lever, and that this 300 is pushing it down, and then this RCY is pushing it back up. And because it's not floating up and it's not falling down, it's 0. So it's static. So we're going to say the sum of the moments about point A is equal to 0. And that's kind of our base of everything that we're going to do here. So I can add in this here and say that 0 is equal to tau at point B plus tau, or torque, at point C. So it's equal to the sum of both of those things there. You can write that in again, 0. And at point B, right here, the force is going to be negative 300 pounds times, and then the distance, which is 3 feet. Very good. And then I'm going to say the next one, which is this right here, tau at C, or the torque at point C, which is over here. And this one we do not know the force yet. And that's what we're solving for, is this one. So it's RCY times, and then the distance, which is 9 feet. Like that. Very good. And now we're just going to kind of start simplifying. I'll zoom in just a little bit for you so you can see my handwriting a little bit better. And say 0 is equal to negative 900 foot-pounds, because we multiplied negative 300 by 3, plus RCY and 9 feet, like that. So I can move this one over. I can add 900 to both sides, plus 900 foot-pounds. Those cancel. I'll add it over here, plus 900 foot-pounds. And it becomes 900 foot-pounds is equal to RCY times 9 feet. And now I can divide, I'll move my paper a little bit for you. I can divide both sides by 9 feet. that does, it cancels that completely, cancels this and the feet, it gives you 1, so it becomes 100 pounds is equal to RCY. And that seems like we've got the right answer. So I'm going to box that. And over here, I'm going to write that in. RCY is equal to 100 pounds. Not too bad. Okay. So there we go. We've got that. It looks great. I'm going to go over here now, and I'm going to do the next, which is the sum of the moments. Or not the sum of the moments, but the sum of the forces about Y in the system. So then, that's again adding this, this, and this. And we know this one, and we don't know this one. So if we know these two, we can calculate for RAY, which is the remaining one. So again, I'm going to write sigma of the forces in the Y direction. So adding up all of the forces, positive and negative, should be equal to 0. So I'm going to write that in here, just put that as 0 is equal to RAY plus RCY, and then plus force BY. So, and then if you're missing that again, it's just the reaction at point A in the Y direction, reaction at point C in the Y direction, plus the force in B in the Y direction. So all in the Y direction on this one. So I'm going to say 0 is equal to RAY, which we don't know, plus RCY, which is what we just solved, 100 pounds, plus FBY, which is negative 300 pounds, which we do not know just yet. So, or I mean, we do know this, we don't know that one. So we're going to go ahead and simplify this a little bit. So we get 0 is equal to RAY plus negative 200 pounds, which is great. And then we can add 100 to both sides. Or sorry, 200. So plus 200 pounds. Those cancel. Plus 200 pounds here. And we're left with 200 pounds is equal to RAY. And that's our answer. So it really isn't very difficult. It's simple math. The hardest part, or that scares most students, is just all of these, like the logic behind why we picked these numbers and these values. But it's not too bad. So once you've gone through this a time or two, it'll start to stick. So down here, I can start writing in these values. So RBY was up here, negative 300. Write that in. Negative 300 pounds. RCY was the first, or first one we solved, which was 100 pounds. RAY was the one we just solved, 200 pounds. RBX, because there's nothing happening in the X direction, we're just assuming that there's like no earthquake or that the heat is now stable and that kind of stuff. It'll just stay at 0. And then RAX, same thing, nothing's happening, so 0. And then RCX, this one, because it's a rolling joint, it does not have a reaction at all. It doesn't have any bolts there, so you just like that, you're done. And that is the whole thing. So when you're all done, your paper should look like this on part B, and it should look like this for part A. So even if you get the right answers and all that stuff just by reasoning it out, that's great, but the part I'm really concerned about, and the part that you're getting the points for, is just being able to do the math and prove that you can do it. And you can follow on with this and all that good stuff, but it's the process we're trying to learn here, not the product. So, okay. Anyway, thank you for watching, and I don't know. Way to go. This is a tough thing, and you did a good job getting this far. So, kudos to you.